Alrighty, welcome back. We have to finish this topic on volume of prisms and cylinders and all that good stuff. And we ended off talking about the formula for the volume of a cylinder. And it works the exact same as the volume of our rectangular prism, if you remember we looked at last time. So the way we're going to go about this is we're going to take the area of the base and we're going to multiply that by the height. Now for a cylinder, that base is a circle. And if you recall from Math 10, the area of a circle is pi times the radius squared. And my height is represented by h. So you have now a quick formula for the volume of any cylinder. Okay, and we're going to use that in a couple of examples down below. So example 2 says, indoor climbing walls have polyester climbing grips inserted into the wall for climbers to grasp. A mold for a cylindrical grip, cylindrical being the key word, they tell me what shape I'm using, has a radius of 1.5 inches and a height of 3 inches. How much material do we need to make this grip? And we're going to round that to the nearest tenth. Since we're told that it's a cylindrical grip, we know we're going to use our volume formula for a cylinder, and we are given the dimensions of radius and height in the question. Now if you want, you can include them on your picture. So here's 1.5 inches and my height of 3 inches. So if that helps you visualize this object, by all means go ahead and label that picture. And what we can do is insert our numbers, so radius 1.5 inches squared, and we'll multiply that by the height of 3 inches, and our volume turns out to be, to the nearest tenth, 21.2 inches cubed. So remember, we are working with volume. We do need to have whatever our units are cubed. Area would have been squared units. So there's how you would do example 2. Now example 3 throws a bit of a wrench into things. So a few videos ago we talked about dealing with surface area. And basically what that was the area of all the surfaces exposed to air. So if we look at this picture now, we have a solid piece of wood with a hole going through the center, which means we've now created 4 additional surfaces to account for, but we've also subtracted 2 surfaces, and we'll dive into that as we look at this problem. So first, what we're going to do is figure out the surface area of the large rectangular prism. So let's say the surface area large, and if you remember, our surface area formula was 2 times length times width plus 2 times length times height plus 2 times width times height, whichever combination you like. And we'll go ahead and put in those numbers. So 3 by 5, so we're going to go 3 by 5 first, plus 2 times 3 by 7, and the last combination is going to be 2 times 5 by 7. Make sure we have all of those in there. And if we were to simplify it, we're going to get 30 centimeters squared plus 42 centimeters squared plus 70 centimeters squared. And in total, we get 142 centimeters squared for the surface area of the large prism. Now we have to deal with the fact that there's a hole. So outlined in red, you can see a second prism. Okay, the 2 pieces that are getting cut out are the small squares on the ends. And we have to add in the other 4 rectangles. So in red, we're going to say the area small squares. Now you can organize this how you like. This is just one way that works for me. So the area of my small squares, there are 2 of those, and I do have to find the area by going length times width. So we're going to go 2 times 0.5 times 1. And the area of those small squares is going to be 5 times 2 times 1. We are just going to get 1 centimeter squared. So this is the area that I have to subtract. I have to take that one away because technically those pieces aren't there. I have a hole. And in blue, let's take care of the other 4 rectangles. So let's say the surface area of added rectangles equals. Now I do have 4, but all 4 of them cannot be the same. One is going to have a height of 0.5, one is going to have a height of 1. So we're going to have to make sure we account for those. So 2 times length times width plus 2 times, let's say, length times height. Okay, so 2 times 0.5 times 7, because that hole goes straight through the box. So the 7s have to be the same. Okay, we're going to add to that 2 times 1 times 7. Okay, so in total there, we get 7 times 0.5 times 2 plus 14. So we get 21 centimeters squared. So we have to add these in, so we've created additional surfaces now. All right, so in total, we have, let's do that one in purple. Total, we have 142 centimeters squared plus 21 centimeters squared minus 1 centimeter squared. 142 minus 1 plus 21. So we have 162 centimeters squared as our total surface area. Okay, so a little bit more complex because I have to deal with that hole in the middle. And now let's look at the volume. Volume is going to be much, much easier to work with, as it usually is. Surface area is generally the more difficult question. So if we're asked to determine the volume, again, we're going to look at the large prism and the small prism. So since the small prism technically is not there, we're going to find the volume of it and subtract it from the volume of the large prism. So we'll go volume large is equal to length times width times height. And our large prism has dimensions of 3 centimeters by 5 centimeters by 7 centimeters. Okay, so our volume ends up being 105 centimeters cubed. Fix that 5 there. So 105 centimeters cubed, so the volume of the large one. And the volume of the small is again length times width times height. And our dimensions are changed, so we have 0.5 centimeters by 1 centimeter by 7 centimeters. Okay, so that small one is only 3.5 centimeters cubed. Volume small. Okay, so what we're going to have to do is subtract those two values to get rid of the volume that's not there, and we'll round to the nearest tenth. So 105 centimeters cubed minus 3.5 centimeters cubed, and we get 101.5 centimeters cubed as my final volume. Okay, so as you can see, volume much, much, much easier to work with. Okay, one more example just to finish off this section, and we'll end the video there. So example 4, a cylindrical swimming pool is 7.5 meters in diameter, important, and has a depth of 2.3 meters, also important. What quantity of water is required to fill this pool to the nearest tenth? We need to know what quantity means in this context. So I'm talking about an amount to fill something, and we talked about volume being the amount of space inside something. So if you're ever asked about a quantity being used to fill something, that means volume. Okay, so you're going to have to look at the volume here. Okay, so if 7.5 meters is my diameter, my radius means I cut that into 2 parts.
Can we use your classroom for China?
Sure. If you don't mind me recording a video that you're now all in. Okay, yeah, sure. Okay.
Where's the first thing?
Okay, so my diameter is 7.5. So if I divide that by 2, it now becomes 3.75 meters. Depth is going to be the height. And my height goes here. Basically, it's how tall the pool is. Okay, so I have a height, I have a radius, and I know the volume of the cylinder is pi r squared times h. I have all the dimensions I need, so let's go ahead and fill that in. So pi times the radius, which is 3.75 meters. I will square that value, and we'll take 2.3 meters as our height. And if you were to grab your calculator, punch all those numbers in, we are going to get 101.6 meters cubed. And that finishes up all of our stuff on volume of prisms and cylinders. The next time that I posted video, we'll deal with cones, pyramids, and spheres, and how we look at the volume of those. All right, we'll see you next time.